Hi, my name is Bert Dicht. I am Vice President of Membership for the National Space Society. And on behalf of Larry Ahern, Vice President of Chapters, I want to thank you for joining another in our series of NSS Space Forums and Town Halls. Our topic this evening, a modern day space elevator 2021. So again, we welcome you to our virtual space forums, a series we started last year. And we look forward to more of these as we go forward. I'll be sharing our schedule in just a minute. But as those who've joined us before, I usually go through a quick ritual and starting off with our virtual etiquette. So to submit a question, use the Q&A function. It's best to use that for your questions because that can be seen directly by the panelists, our speaker, and also our moderators. So we can submit and get those questions answered. You can use the chat function to make comments. I would urge everybody to be respectful because they can be seen by the panelists and the audience. But if you do submit a question in the chat, we have to find that and sort it out. So again, it is better to use the Q&A function for your questions. As you're viewing, we'll have this in speaker mode, but it's also best if you have it in speaker mode as well. So that way, whoever's speaking will be up on the screen if we're not sharing the screen. Our agenda for tonight, as always, we go through a series of announcements. We'll talk about our upcoming space forums, and then we're going to get right into the presentation. So if you just bear with me, and then we'll close out for this evening and wish you all a good evening, of course. So our announcements, as I like to say, just remember to check out our website. Oh, looks like that advanced ahead of me. There we go. Check out our website on space.nss.org. And we are constantly updating it, and you can also catch our blog. If you are a member of NSS, make sure you check out inside.nss.org. That is our membership portal that gives you access to a lot of things to help you take control of your membership. We have a YouTube channel, a Facebook page, and also a Twitter. And also we have an Instagram. We'll be adding that to show you as well. So check all those out and you can stay up to date with what's going on in NSS as well as what's going on in the space program. I always encourage everyone to give to our cause. We're a not-for-profit organization. So if you enjoy our programming like these space forums and town halls, please make a donation. go.nss.org/donate-now. I will put that link into the chat. So we welcome all donations and we thank everyone who's made a donation previously. It really helps us out and to provide programming just like this. I also encourage you to complete the post-space forum survey. It only takes a couple of minutes or only a few questions. It's anonymous, but the feedback really does help us with our planning and trying to figure out what we need to do to make these even more valuable to you. So let's talk a little bit about what's coming up next. In 2 weeks from tonight, on the 3rd of June, we have Emily Carney. She is a frequent author in our Ad Astra magazine and our blogs and other space magazines. And she's also the founder of Space Hipsters on Facebook. Her topic is Gerald K. O'Neill and the Future That Calls. And actually, if you had the most recent issue of Ad Astra, you could see her article about Gerard O'Neill. So look forward to that. It's going to be really interesting. And I know our speaker tonight's going to be touching a little bit on Gerard O'Neill as well. So it's a nice tie-in. Upcoming after that, on the 17th, we're going to have a preview of the Virtual International Space Development Conference. And the conference will be held a week after that. I've put in the link, and I'll put that in the chat as well. It is active now, so you can see a list of speakers. A lot more that information will be coming about how to sign up and join for that. A lot of great topic areas and speakers over those days. So we hope you can join us. If you join us on the 17th, we'll give you a good preview. We are still working on our speakers for July. In August, we've got a couple things lined up already. On the 5th of August, we have the NASA Marshall Space Flight Center speaker talking about the SLS. And I know a lot of you will be interested in that. 2 weeks after that, we have David Chudwin, also a longtime NSS member. He was actually at the launch of Apollo 11, covered it as a teenage space reporter, and he has a book out about his experiences. Fascinating, fascinating story. So be sure to join us for that as well. And we're working on September. So please join us for all these upcoming events. The program tonight, I know we've talked a lot about rockets. Tonight we're going to talk about a different way to get massive payloads into space. A modern day space elevator 2021. And our featured speaker tonight is Peter Swan, PhD. Peter has a long distinguished record in working in the aerospace industry, a retired Air Force officer, and now the president of the International Space Elevator Consortium. So we're looking forward to his presentation. I also encourage you to check out the website of the ISEC. A lot of great information is there, and I'm sure Peter will tell you more about that. So Peter, I'm going to turn it over to you. We're looking forward to a great session.
Well, thank you very much. Let me get this share thing going, and we'll get going here. Okay.
We see it.
Well, I want to welcome everybody to the excitement of the future. The NSS vision is vibrant and bold. It has been with us since Dr. O'Neill and the L5 Society. I was there as a junior space engineer. I even made it to the Apollo 12 launch at one time. And I remember the magazines and the philosophy and the preliminary discussions about how we were going to do an off-planet colony. There was so much hope in those days about where we were going off-planet. As you can see, my credentials, I put all my credentials there just to add a little credibility and the long list of accomplishments. The bottom line, though, really, if you think about it, is I'm old, and you got to be able to do something in all those years. But anyway, those credentials should open up the following discussions. And the discussion should center around the statement that massive movement of manufactured components to the L5 colony can be accelerated during the 2040s, leading to the initial L5 colony by the 2050s that would be enabled by massive movement of cargo from the Earth's surface by space elevators. To accomplish our vision, both NSS and the space elevator vision, we need a permanent space architecture. With my credibility as a 50-year space engineer who has been there and done that in so many areas, I state that the modern day space elevator can be accomplished. Our company, Galactic Harbor Associates, has started the process. Today's presentation, hopefully, will start the discussions. But first, 2 or 3 items. I have been teaching for years and have to share it. I like to share a lot of information. So on my charts will be a lot of stuff. Please absorb the message from each chart and then go back later to review the details. This presentation will be on the NSS YouTube site in the near future, and hopefully I'll get charts to Bert so you can actually have access to the chart. In addition, most of my statements tonight are backed up with engineering and scientific reports and data on our website. Okay, now I got to get this going here. Okay. This chart is to remind us that we're looking at the future from across the country and around the world. And of course, NASA, European Space Agency, Canada, and others have signed up to go to the moon in the first half of this next decade. And I love that. The bigger promise is to encourage and include the diversity of all humans, especially our youth, to think beyond the local horizons. In addition, we should encourage and support the commercial ventures committed to support these movements off planet. Our visionaries are out there. Now we need to encourage and support and reach further. Jeff Bezos' comment about building a road to space is probably as good as it gets. Mr. Musk, multi-planetary, that's right on. NASA's first woman, next man on the moon, living and working in thriving communities beyond Earth, remarkable. And then, of course, there's John Mankins. We're going to talk about him a little bit. He wants to stop global warming from space. Space solar power constellation will eliminate thousands of coal-burning plants. A remarkable concept. We can help them with that. So our new vision of the space elevator community is we want to have space elevators as the green road to space. Essentially, if you lift your payloads with electricity from the sun, it's pretty green. While they enable humanity's most important missions by moving massive tonnage to geo and beyond. So tonight we're going to talk in three parts. It's pretty straightforward. The first is, why are we doing space elevators? I love that part. Then we're going to get into where we are in development. I said we're starting the process in our little company. That's true. Then we're going to talk about how space elevators and advanced rockets work together. The mandatory, it's a complementary and compatible arrangement of strengths. Now, remember, the space elevator is the green road to space, and they move massive cargo. If you remember those two parts, massive cargo and green road, then you can understand why we must build space elevators. So the bottom line is, why build them? And the answer is because we can and we must. Space elevators will fulfill the dreams of many. We can build and launch liftoff massive cargoes using solar energy, green road to space, permanent infrastructure, daily, routine, safe, inexpensive. But here's the kicker. 30,000 tons per year in the initial operations. Now, wait a minute. I have a chart later that I'll show you that we've done 22,000 tons in the history of mankind to orbit. Everybody talks kilograms when we're talking about delivery, not tons. So we're talking 30,000 tons in the first year of real initial operations, more than humanity's put up between 57 and 2020. Elevators are simple, elegant solution to the rocket equation because they avoid it. I'd like to quickly look at the chart on the left. This is our dual space access strategy. Space elevators and advanced rockets. But I also want to mention that Amelia Stanton was our summer intern. She was a student up in Scotland. She did that because she understood the concept better than everybody at ISEC. She figured it out. She painted that in acrylics. Amazing that a young college kid actually figured out our strategy before we did. No, don't tell her that. Anyway, O'Neill's vision. Man, oh man, this is fantastic. This is where we're going. A colony off planet. The question is, how soon can we get there? And if we use space elevators, we can get there in the 2050s. Now listen, here's the deal. When they calculated how much mass they needed, they were talking 10,500,000 tons to L5 for several million people. 10 million tons. Now we've only done 22,000 tons in 60 years. So let's keep using rockets, right? No, we want to use rockets for what they do best, moving people through the radiation belt, going to LEO, go to other orbits. The NSS vision is driving us. The NSS mission is what we need to do. When the two organizations merged, I don't know when that was, in the 70s or 80s, we actually took on the challenge of having a multi-planetary off-planet species. And we need to get back to that thrust. Glazer's vision is remarkable. I want to congratulate Dr. John Mankins, who has taken that as a passion, probably 15, 20 years now. And he's got it to the point where he has contracts to start building hardware to go into low Earth orbit prototyping. He is doing a great job, but he needs 5 million tons of geosynchronous. He and I talked about that in the 2019 IAC in Washington, and he gave me the numbers, signed in the bottom line. Now, those numbers are based on his Mark II version. It turns out just in the last week or so, he's released a new design, the Mark IIIA, which is 7,000 tons instead of 98,000 tons. So save yourself 20%. 5 million minus 20% is still a lot. So we're talking about space solar power. Here's John's plan. He's got it in the plan. Low Earth orbit prototyping, then move up to geo, then make a bunch of them and save the planet Earth. I love that. It's a great plan. So if you look at what we need, this is a project done by the International Energy Group. I don't know. I've got the numbers and names in the report we did. But that's a projection of needed electrical power. The little arrow up there to the right is what we need in about 2050, 2055, double or triple what we have now. So all this data came up and it says we need a lot of power. Remember, it's 5 million pounds to geosynchronous. Mr. Musk stood up and said, oh, I want 1 million people on Mars. I want a multi-planetary species. Oops. Million metric tons to support his colony. Okay, so now we're talking about 5 million, 10 million, 1 million. Mr. Musk has a very good plan on doing it, and I applaud him. I think he's doing a marvelous job. It is remarkable, and his vehicles are just surprisingly good, and I really salute him for what he's doing. But let's all make sure we got it understood. He wants 100 tons delivered to Mars by each vehicle. But that's the mission vehicle over here. He needs the mission vehicle launched and 4 others launched with supplies and fuel. That's 5 launches to make one guy go to Mars. So that's a lot. So that's launch after launch. Now, definitely he's going to use reusability and he's going to do a spectacular job. His vehicles are going to be remarkable. But remember, the rocket equation doesn't care about cost, doesn't care about reusability. There's no cost factor in the rocket equation. So you still can't get more than about 20 metric tons en route to Mars with huge launch. So the reference missions we're talking about here are very simple. I kind of explained them one at a time, but it's basically 5 million tons, 500,000 to the moon village, 1 million to Mars, and 10 million for us National Space Society people that want a off-planet capability. So what we propose is the rockets are here now. Let's let them open up the whole ball of wax. Let's let them put the first people in the gateway and the first people on the surface of the moon. Let them go to Mars and do that. But let's plan on the space elevators coming in at about 2035 and moving the heavy stuff. So let's not waste time moving heavy stuff until we get our big tractor trucks there ready to do that. This is a little chart I put together. By the way, I don't care if it's 50% off. If anybody can improve that chart, I'd love it. I spent about 2 days looking for that, researching all that stuff. You notice the space shuttle is the heaviest dude there, 16,000 tons, most of the mass. And that's what made it to orbit. The space shuttle was a launch vehicle and an operational vehicle. So I counted them as mass. 22,000 tons is all we put up since 57. Even if that's off by an order of magnitude, we're still way low. And here's some demands that we need to talk about. A report was done in 2013 that summarized what the future was looking at. And we're talking 174,000 tons needed to move to orbit by 2045. Those are just numbers that have come up from so many people around the community. So our visions are great, but we don't quantify the visions very often. Very, very few people actually put the numbers down. What do we need in orbit? Okay, let's talk about our best success here. I love this. I'm a space geek because this was there. In fact, I even contributed a wee bit to the space activities for Apollo. Of course, I was 42 levels away from anything that counted, but I contributed and I felt good about that. Everybody loved the Apollo program and it was remarkable. How hard was it? It was really hard. We had so many good people working on so many different problems, and we had really tough issues we had to figure out. We did. We made it work. It was remarkable. And it's just, you know, one of those things that changes humanity. We went there and we did that, but it was big project. So let's talk about the numbers. I've been a numbers guy here so far this morning or this evening here. Apollo launched 3 million tons, 3,000 tons off of the planet. It delivered 0.5% of that to the surface of the moon. In other words, your delivery process is to deliver 0.5% of the mass you started with. Now, if I were Amazon and I wanted to deliver a package, that would be unacceptable to any place on the surface of the earth, but we had to go against gravity. So that's the way it worked. See the little Apollo capsule up there that landed in the ocean? That was less than 2% of the mass at the pad. Why did we do that? Because we couldn't do it any other way. That's the way we had to do it. The rocket equation came in and ate our lunch, but we did it. We were successful. It was remarkable. I love rockets. I've worked on rockets. They are remarkable vehicles. They're just phenomenal. There are some other numbers, just anybody wants to play with those. Here's a bunch more numbers. You can check these out. As I said, I try to put more information into my presentation than I actually talk about. But if you look at the percentage to the different places, not very good. We don't have a good record of delivery. Now, we just launched the Mars 2020 and the Hope to Mars. They were less than 0.5% of the mass at the pad. That's really sad story. It's the only way we could do it. There is no other solution. We must use the rocket equation. So we have to. So I calculated Mr. Musk 1 million tons to Mars, and I might be off, divide this number by 2, whatever you want, I might be way off. But my numbers come up 40,000 launches to support his million people on Mars at 1,000 launches per year. Let's think about that a little bit, people. 1,000 launches per year. We barely had 100 launches per year over the last 35 years, maybe 120 average, something like that, 100 launches a year. He wants to do 1,000 per year. Now, I love Mr. Musk. He is super good, and he does what he says he's going to do. So I don't doubt he can do 1,000 launches a year. And I support that. But man, oh man, 1,000 launches a year. So here's a conundrum of rockets. The question boils down to, would you want to employ a methodology for delivery that only delivers less than 1% of to your desired location? That's the puzzle. Do we want to depend on a delivery system that only gets 1% or less to your delivery location? Now, right now, it's the only way to do it. There is no other way. Teleportation is really, really good. I'd love that, but we haven't figured that one out yet. So my answer is space elevators. So our dream is humanity moves off planet. That's the National Space Society. It's the L5. It's Mr. Bezos. It's Mr. Musk. Everybody believes that, and we want to do that. And we have a huge vector going that direction with the NASA commitments, European Space Agency jumping on board, the other countries joining us. We are going to the moon. In fact, their vector is to the moon and then on to Mars. So we are going there. But I keep mentioning the rocket equation and people don't want to talk about it. Here's our vision. We would like to have our galactic harbor. Now, we've defined galactic harbors. It's a new term. It's been around about 3 years. By the way, you can check it out in one of our International Space Elevator Consortium year-long studies. But it's 2 space elevators radiating out from the Pacific equator, basically south of Honolulu. It goes outward, and then you have a tether that supports 7 tethered climbers between the surface and geosynchronous. And they go up to geosynchronous and offload there and float over to their mission areas, or they continue out to the apex anchor and are released from the apex anchor at 100,000 kilometers up. Now, here's the reason you want to do this. There's 2 reasons. One is a green road, we're lifting with electricity. And the second is we're going to move massive tonnage. If you look at those 6 elevators, and by the way, we come up with 3 times 2 because there's going to be competition. Whoever owns the first space elevator is going to have one heck of a leg up on space. They're going to be able to put anything they want up in space very easily. So we have 3 with the competition, and we'll get like 30,000 metric tons in the first year if they're all operating initially. And then as we upgrade each of the tethers, we believe we can upgrade them in like 5 to 10 years. We could get up to 173,000 metric tons per year. So we could supply Mr. Musk 5 million tons in like 5+ years. So we're talking about massive movement. That's not even discussed with rockets. There's a history chart on the upper left, and the lower right is that growth of off-planet movement by using space elevators. We grow 1, 2, 3 galactic harbors, and then we grow 1, 2, 3 galactic harbors, advanced technologies, stronger tethers, bigger tether climbers, all that kind of stuff. Now, here's a chart I just want to show you that we did. It's in our report, The Green Road to Space, on our website. The green line is Dr. Mankin's goal to stop global warming. In other words, to eliminate like 1,000 coal plants. Okay, that's an objective. Now, the slanted one above that is better. Okay, he wants more than 12%. The orange line is 1,000 launches per year of something like a Elon Musk big rocket or a New Glenn or something like that. It never catches up to the need of electricity. But if you take the blue line and you take the space elevator and you ramp up according to our numbers in the previous chart with the improving space elevators for 3 galactic harbors, we can match the needs of humanity by 2060, pick a number, 2067. And we can have significant impact before then. We're ramping up real fast. So we can deliver the space solar power satellites to geosynchronous in a rapid manner. He needs 5 million tons. We can do that. Okay, so each one of these segments of the presentation today have questions that were submitted earlier, and I've incorporated them into answer these. At the end of the day, we'll jump into some other ones. Okay, there was commented, and I think this is very appropriate, that Mr. Jerome Pearson was the inventor on record of the space elevator. That's almost precise. Yuri Artusanov in 1960 invented the space elevator. Jerome did it in 74. They met at our conference in like 03 together, and they talked about it, and neither one knew the other, and neither one used anybody else's work. So we consider them co-inventors. But the suggestion is that we would name the space elevator after Jerome Pearson. If the Russians do the space elevator, they'll name it after Yuri Artusanov. Okay, some questions. What is the applicability of the lunar and Martian surfaces? Fantastic. I believe we need space elevators on all celestial bodies to beat the gravity well that you're in. But here's the kicker. If we don't get off the Earth, if we can't beat the gravity well on Earth, we'll have no robust growth outward. So having a space elevator on the moon and Mars is kind of like not really necessary. But if we can have a space elevator on the Earth, then we're going to need space elevators on the moon and Mars to accept the massive inputs. So yes, we need them on all planets, but Earth first. When do we visualize it to be a reality? 2038. Estimated cost, $15 to $20 billion, not too much. But here's the kicker. The infrastructure is not good business. People who invest in the first, mall or something get in trouble. But overall, the economics are remarkable. Think of a bridge going to the San Francisco Peninsula, and you put the first bridge into San Francisco. Think of the housing and all the money you got from the economics of the new city. And then, of course, how many tons of cargo deliver to Leo each day? Whoops, misconception. Space elevators don't deliver to Leo very well. First off, we're equatorial. Second off, at the Leo altitude, we're not going very fast. So if we drop off, we're going to go straight down. So you have to go up and then you drop off, and then you got to use rockets to circularize your orbit. Oh, then you got to use rockets to put it into an inclination of useful orbit. And so Leo's really not our friend. We don't want to do that. Rockets are very, very, very good at that. They get 4% of the cargo to Leo. So let them do that. We go to Geo and beyond, and we do it superbly. Okay, part 2, space elevator development. As I said, we're ready to start. So let's start here. First off, we've got a whole bunch of reports, 1-year reports that are on our website that address almost any issue you want. If you go there and ask a question, you can find a report that'll answer it. There are also 3 reports out there that were international. The International Academy of Astronautics did 2 of them. 2014 kind of looked at TRL levels. 2019 looked at how we would do it. The space elevator construction concept by Obayashi Corporation is remarkable. This is a big commercial company said, I want to build a space elevator. Let's go think about it. Green Road to Space is the latest one we've published. Bottom line is we lift off with electricity, and we can enable things like space solar power, which will be greening of the Earth. So we have 2 factors. One is we lift off with green, and the second is we enable green missions. Elevator strengths, most people understand this. It's basically routine, safe, inexpensive, permanent, 24/7, et cetera, and massive movement of cargo. But we recently did a study with ASU, Arizona State University, and they came up with some remarkable results. The first is, and that, by the way, that study's also on our website. We could toss every day of the year toward Mars. Now, some trips are 400 days, some trips are 61 days. By the way, fast transit 61 days. But we can release every day. There's no 26-month wait. If you want to send hammer and nails, you go on the long trip. If you want to send pizza, go on the short trip. But we can have a bus schedule from our space elevators going to Mars. A remarkable concept. Just lift off, go up there, let loose, get there in 61 days. Plus massive amount of cargo. So we can really do something. We can enable Mr. Musk 1 million tons to Mars. Okay, where are we? We believe we've shown the technological feasibility of the system, TRL levels, all that kind of stuff. The breakthrough was recently we determined that we have a material that will work. Now, Mr. Adrian Nixon works in the University of Manchester area on single crystal graphene, and he has stated that it will be there for the space elevator tether. Now, we're not going to need it for 10 years or so, maybe 8 or 9 years, but he said it will be there. It's a single crystal. We're going to talk about that in a few minutes. So we're ready to charge ahead. We're ready to take on the world. And our strategy is dual space access architecture. We want to go to space with rockets because rockets are really, really, really good. They are a remarkable tool. They've got great strengths. They do LEO really super, move people through radiation belts really great. They do a great job. But their visions are restricted by the rocket equation. So we want to build a methodology to move mass. 70% of the mass on the pad goes up. By the way, the other 30% are tether climbers. We reuse those. So you could say 100%, but anyway. So we're going to be slam dunking the old concept of 2% delivery to geosynchronous. The promise of space elevators is so remarkable, we should not wait. So the permanent space infrastructure. Whoop. The approach is dual space. The result is a permanent access to space with both schedule up a rocket launch, schedule up a liftoff from a space elevator. So it can work in either way. Okay, now we're talking about the material. It turns out the material is a restrictive step in the development. We have jumped the river. We are ready to go ahead because the statement has been made that I can make single crystal graphene in a continuous process to be real to real. I heard that from a scientist who is at a company called General Graphene. So we are able to do that. Now, they haven't done that yet. They've done it with polycrystalline graphene, which is very similar to single crystal graphene in the process. So the processes should work with both. We are in the development phase of having a material for space elevators. If you look at the chart on density versus strength, you can see all your favorite stuff there. And then you can see that CNTs were supposed to be really good. We just can't grow them in long lengths. But graphene fits right there in the same place. So if we can have reel-to-reel continuous production of a single layer of single crystal graphene, we can fulfill our needs. And they say they can do that. Adrian Nixon's on our board, and he states that single crystal graphene is strong enough and is a candidate for the tether material and should be ready for us when we need it. This is what it would look like. You would send in methane. The temperatures would separate the carbon from the hydrogen and all that kind of stuff. And the carbon atoms would combine in a 1 atom thick, 2-dimensional material that would then be reeled out onto a roll by roll. Okay, so let's go back to one of the basic strengths of space elevators, and that is that it's green. Our report showed very nicely that we could enable all kinds of missions to great locations with mass by using electricity to raise the space elevator tethered climbers. No burning of rocket fuel or anything like that. Space-based solar power would be enabled by our ability to deliver mass. They can't do it right now. They can do all kinds of prototypes, but they can't get to 5 million tons of geo in any reasonable time frame. We can deliver high-level nuclear waste to an orbit, a low orbit around the sun, so it will never bother humanity again. And we can repair and refuel at geo almost anything you want in a green manner with almost no expense. So we're talking about the capability to do all kinds of things in an environment. Okay, how do we get space elevators in place? It's very simple. We use our friends, the rockets, to get us to geosynchronous. And then we run a string down and let the center of mass stay where it's supposed to be, but there'd be an equivalent mass above it. And then you'd let more string down and you grab it at the equator down in the Pacific. Right now, we're looking at the Pacific south of Honolulu, but basically on the equator. And then you have a mass up at the top and you have it reach a little bit further out. So there's a continuous stretch outward. And that's like having a rock on a string around your head and tossing it around your head. Centrifugal force pulls it out. And so therefore, you're going to have a tension in there. You move it out a little further, you get greater tension. And then you can, now that's your single small tether. Then you run tether build-up climbers up the tether and build up the material. And the last time I saw any numbers, it was like 274 little climbers to build up to an operational tether. I have no idea whether that number is close to the right answer, but the concept is pretty straightforward. And then you can use your space elevator with tether climbers and do what you need to do. And then as you go forward, you would also build up the tether climber to have more capacity, more capability for each tether climber. So that's the concept. We see 6 of those tether climbers around the world in 3 galactic harbors. Now, the mass to orbit is the major barrier. So let's use the example of space solar power. We've got most of these numbers from Mr. Mankin's activities on the web and the reports and stuff like that. His Mark II A system is 2 gigawatts and basically 10,000 tons, 9,700. He's got a new one out, but we didn't put the numbers into the presentation because it's just like the last 3 or 4 days I got the word. Anyway, so Mark III does the same 2 gigawatts, but it's a little less. So we're really talking about a bunch of mass, 500 launches at 20 tons per launch. 20 tons per launch, 500 of them. Bummer. So that'd take you a long time to do that. And if we have a dual space access, where we're using both rockets and space elevators, we could have rockets delivering the first versions of space elevators, first versions of space solar power up there to prove the point and show that it works and start the environmental effect. And then we start moving the huge masses by the space elevator. When we have the huge masses moving, then Dr. Mankin's constellation fills out pretty fast. Okay, so rockets and space elevators are complementary technologies for our missions for moving off planet and saving Earth. So we call it dual space access architecture. Here's a quick little look at our ASU study. If you go up the space elevator to 100,000 kilometers and release, going 7.76 kilometers per second, you can actually reach Mars in 61 days when the planets are aligned correctly. If you go up higher and have a longer space elevator, now nobody said it can't be longer. We've just optimized it 100,000 kilometers. Look at that, you get almost 50% more velocity. There's a study done by our professor at ASU, Dr. Pete, and he's got approaches for the space elevator release that literally you can leave from the end of this tether and leave the solar system. You have enough velocity from the space elevator to leave the solar system. You think about that a little bit. How much did we have to do to get Voyager to leave? I think it was 3 gravity assists, big rocket, everything else. Anyway, the point is we can do different things with space elevators because of the strengths of the way it works. It's just a little pretty picture to show that we really, really can do some different and better massive movement. So it's a green road to space massive movement. Okay, I went and I searched this on Wikipedia to just see what they're talking about out there about what we're going to do in the future in space. Well, if you think about it, there are a lot of things they want to do. Lunar, interplanetary, solar power, all kinds of stuff. This doesn't even approach discussing about how the constellations of GEO want to expand. We've got constellations for METSATs at GEO, all that work at GEO that we could do better if we could lift stuff inexpensively, routinely, daily. We could really increase the capability in all the orbits. Okay, the second part, the development, we have some questions from the audience. What will hold the structure stable? Centrifugal force. Okay, where would we build it? The equator, south of Hawaii. The reason is we want the minimum weather. And if you're on the equator, all the hurricanes are north and south of there. The place we looked at has had no rogue waves, no lightning in 100 years. In addition, we want to be in open water, so there's no legal territories that would think about taxing us or anything like that or taking over. So we'd want to be in the open ocean. Single crystal graphene is going to be really remarkable, 150 gigapascals and stuff. There's some information on our website to talk about that. The whole topic of the material is developing all around the world. The first paper was out of China. We've got the Nobel Prize out of the University of Manchester for the topic. Really is remarkable. We have a very safe approach. We're all engineers, just like bridge engineers. We'll do it so it's a safe approach. We'll register it in our home country. If the US does it, it'll be US. If China does it, it'll be China, et cetera, et cetera. What maintenance is required? Yep. it's like a bridge. We got to work on that. How do you do it? How do you make it work? I don't know. We'll figure it out. But the real question, there are 3 or 4 of these. What about space debris? Okay, we get that question all the time. I agree with you. It is very, very important to understand. We have 2 reports on the web, and we have 1 architecture note covering the topic. So we have addressed this continuously from 2010. Bottom line is in blue. It says space debris mitigation is an engineering and management problem with definable quantities such as density of debris and length width of targets. Space debris is not a showstopper, period, end discussion. 2 studies we've done on it. Now, it turns out on the right, we've got one of our approaches that will probably be real. We don't know how many tethers will be coming down, but from 2,000 kilometers, we'll run 3, 4, 5, 6 tethers down to make sure that the upper part of the space elevator doesn't go away if something's cut. The odds are space debris below 2,000 is where the danger is. Now, I believe it's a manageable problem and we won't have a cut. We've got 3 approaches that we're going to do in parallel. The first is passive, multiple legs. The tether design will be such that it can take a hit from everything less than, say, 10 centimeters. And we'll just have it blow through the tether. And then we'll have a little tether repair climber that goes up and down and inspects the tether and it patches it, stuff like that. The active is the one that you ought to really understand. We can move the tether. It's like a sine wave, a piano wire. What we do is move the bottom of the tether on a little mobile, ocean going vehicle and start a wave. If you've got a tether climber halfway up, you can stop it. You can go up, you can go down, and that will produce forces that will move the tether all the way along. That's all predictable. We're in the process of coming up with the gold standard for the tether dynamics so we can predict it. And then there's the active. We'll have protection. The idea is that if something is real danger, we can go up and talk to it, move it, or we can deorbit it. That's starting, by the way. We've got activities to remove stuff from space. And collaboration. We will be in bed with all the people working space situational awareness and space traffic management. We will be in their facilities and they will have people in our facilities in our op center. There's no doubt about it. We'll be working with them very closely. What we'll be doing is we'll be talking about what and how to deal with the issue. There'll be many, many topics addressed. Debris alerts. We'll want to know when something's coming close. We'll need to size all this stuff and watch all this stuff. And then we'll move the tether, or we could even have people removing space debris if it's dangerous. And, post-event activities, something blow through and set a dynamic movement of energy up and down the tether. We can work on all that. So the bottom line is space debris is a concern. We've got to work it. Now, let me give you just a little background. I tracked satellite debris for a year. I worked on the constellation risk of having low Earth orbit communications constellations called Iridium and what the risks were to space elevators. I wasn't the principal one, Skip Penny was. And we did analysis on whether those guys would be hit. We understand space debris in the commercial sense, and we know how to handle it. But it's still a major concern. There's no doubt about it. We've got to worry about it. So the bottom line, once again, is it's an engineering and management problem. Okay, here's some numbers just to give you a little feel. Let's go down to the bottom line. Okay, we divided everything up into 60-kilometer stretch. And then we said, if it's in a density area here, altitude, we did 60-kilometer stretch elements. And we looked at the density in that element and then calculated the probability of conjunction. We did it for the density of debris in 2010. NASA gave us a density in 2019, and we did it for 2030 when the projection of constellations is up there. We did the calculation for all of them. And the numbers there on the chart assume that we don't move the tether. We assume we're going to move the tether and there will be no collisions over all time. So, we've got the engineering solution, the management solution. We understand the threat. Okay, part 3. Here we go. We got part 3. Space elevators are mandatory. They have to work with space advanced rockets. NASA, they're going to the moon and Mars. Yay, along with all the other countries that have signed up. The NASA plan have 6 big space launch systems and do it. Well, I'm a proponent of that. I want to support them completely. The commercial imperative is out there and doing well. It turns out that Mr. Bezos, Mr. Musk, and the other people competing for the different aspects of the movement off planet, it's a quiet revolution, but it's really expanding rapidly. I love the commercial side. They're doing a fantastic job. There's a little chart that I find interesting. Those are number of launches by countries and everything else. And then the bottom right-hand side is commercial launches. Holy schnuckers. Commercial launches going into space. Unbelievably, never even thought of in the 60s. Here's our approach to go to the moon. And it looks like, you know, all these different activities are here. We want to support this. Look at the second one. I love that, tourist. Who would have thought we'd be sending tourists around the moon? I mean, that's really remarkable. In fact, the last month, I haven't been able to keep up with the number of tourists that have paid big money to go on an Elon Musk Dragon vehicle or to go on a Russian vehicle to go into low Earth orbit and go to the space station. It's just remarkable. It's been happening in the last month. So tourism in space is big time. The dream of humanity to move off planet is ongoing and it's real. And we believe it and support it. NSS is mainstream, trying to make sure everybody understands that's where we're going. And we support NSS in this in all different ways. We believe the space elevator should be a complementary things to advanced rockets. We're inherently environmentally friendly. We can team with rockets for zero emission liftoffs. We can enable Earth-friendly missions. I mean, it is remarkable what can be done if you're just lifting off the planet with electricity. Okay, now, if we want to power American cities, we're using this as an example. In our report, we have other cities around the world and everything else. These are the different systems on the bottom, space solar power systems. They've got a power output and a mass that we relate. And then if we just look at the Alpha Mark II and look at the cities, we would, to do New York, we'd need 2.4 Alpha Mark IIs. That's 10,000 pounds times 2.4 at geosynchronous. I live in Phoenix, so we need 1 at geosynchronous just to handle Phoenix electrical demand. That's 12% of the demand in 2060. So it's just 12%. But we need 1 dedicated for Phoenix. So we're talking about huge masses to orbit. And, you know, each individual one of those cities needs that support. Okay, here's a chart that shows throughput from a space elevator perspective. And we just picked the year when we would be operational and started talking about the mass being delivered to geosynchronous. So let's just assume this was supporting space solar power. Of course, all the other mission people would be yelling at us, no, 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 you got to use some of this capability for me to go to Mars or me to go to moon. But if we're just doing space solar power, that's the amount of tonnage we can move each year toward fulfillment of the space solar power. Remember, he's got to have 5 million tons. So that's really a lot of stuff. We can deliver all these systems in time. And I showed this chart before, but it's interesting to see it again, in that that's our demand curve. And then this, the orange one is 12%, I mean 1/8, 12% of the demand. The red one now is 1,000 launches of rockets going to GEO, delivering 20 metric tons. And then that's our space elevator. That's the difference. That's the difference. Massive delivery in a green manner to support a green mission. Let's put that out there again. Massive support in a green manner for a green mission. I never thought of that before like that, but that's the way it is. That's a good way to say it. So that's the point we're at for 2056. And then we could get better in 2068. And then way out there in the future, we'd have something more. So we're talking about a capability that is really remarkable. Okay, space solar power cost in years. We just came up with some numbers here just to play. If you used Atlas launches and 20 per year, which is about as much as they've ever done, that's 25,000 years. Spaceship, Starship, 20 metric tons to GEO, 1,000 years, 1,000 a year, 250 years. The cost is exorbitant. So really, if you want to do space solar power, you've got to do something besides rockets. You can start the program with rockets. I applaud that. Let's start with rockets. So what we need is a dual space access architecture. We want to start with rockets, and then we want to, whoop, where's my little thing here? We want to start with rockets and get the program going, and then take the heavy mass up with space elevators. So it's a combined delivery approach. So why space elevators? Why do we want space elevators? The answer is they fulfill the dreams of many. How many people have been dreaming of the L5 colony? I raise my hand. Okay. I've been dreaming of it since I learned about it in LA, and I was a young space system engineer, and I said, that's neat. Now I thought maybe we would, move right into that. Didn't quite happen. So it raises massive cargo in a green manner, in a permanent infrastructure, daily, routinely, safely, inexpensively, 30,000 tons per year. The bottom line is space elevators are a simple, elegant solution to the rocket equation. They avoid it. That's the point. We avoid the rocket equation. Unbelievable. Okay, questions for the audience that fill in on this part, which is why we must do it. Really, the bottom line on these questions was, how do I become involved? And I thought that was very interesting that we asked for questions and they said, how can I be involved? And so it's simple. Go to our website, sign up for the newsletter so you can see what's going on. That's simple, doesn't cost you anything. You could join ISEC as a student or as a professional. Volunteer to participate in our studies. We're about to announce a second study. We've got one ongoing, which is the tether climber interface with the tether. What's the friction on the tether? What's coefficient of friction? All kinds of questions about the tether climber and a single crystal graphene tether. Then we're going to move off to do some another study that's going to be started in August, somewhere like that, which is the characteristics of the tether material and how do we test them. So it'll be a test-oriented study. That would be really interesting if somebody wanted to be in the testing arena. We have other things going on, so send your name in and volunteer to participate, and we'll see what your skill set can do to match ours. The other thing is about Jerome Pearson. I really like that suggestion that maybe we could help, move on to the idea that Jerome Pearson would be the name of the space elevator that we develop in the South Pacific. I'm going to have to propose that to the board and see what they think. Okay, we now have, look at that, 1 hour on the nose. We now have 15 minutes for Bert to read questions from the audience. I'm open for whatever you want to say.
Very good, Peter. Let me see, I'll go to it. If you want to stop sharing so we can.
Okay.
Yeah. I know we've got quite a few in, and there's been some great discussions going on in the chat as well. So I'll have to see if we can cover all of this in the few minutes that we have. So let me start with the questions that have been submitted. And I think you might have touched on this. It's not really a question about space elevators, but it was about the power density, the downlink from the proposed space solar power station. I know you had a chart on that.
Well, I don't know the answer to the downlink. They've got it designed so it would be safe for, it would come down to a region. It would be probably hazardous to birds flying through, but it would be an exclusion zone for airplanes and people and all that kind of stuff. So it's like a 2-mile diameter collection antenna on the bottom. And it's as safe as any other electrical approach to providing power to humans.
Very good. Maybe we can also pass that on to John Mankins possibly as well. And that question came from Henry. So I'd just like to announce everyone. Got a
Well,
question.
Henry, that answer is in about 32 documents out there. You can go look for it. It's very, everybody asks that question, and it's very real and very serious. And Dr. Mankins is taking that question every time, and it believes it's a question that must be addressed.
Very good. Question from Bradley. Looks like there's two of them. What's the plan and timeline to prove that single crystal graphene production process? And what's its current TRL and confidence level it can advance to the next TRL and ultimately operational capability? What's the TRL? Is that the technology readiness level? I think that's what that is.
Correct.
Yeah. Okay.
Let's just put it the following way. Single crystal graphene has been proved that it exists. It's in the laboratory. It's been produced at about a 1/2 meter long, 1/10 of a meter wide, single crystal, okay? Atom to atom, 1/2 meter long, single crystal. Been produced in multiple locations around the world, China, University of Manchester, other places. The real kicker is we're way, way, way short of any analysis like TRL levels. We are in the scientific development phase. Okay, we got a long way to go. But let me give you some experience from from developing mega projects. Every mega project I've been on, and I've been on two successful ones. When we started, we had these big boxes in the schedule that said miracle required. I remember vividly the one in Motorola in Iridium. We didn't have the speed, and all the chips that Motorola had didn't have enough speed to keep up with the required switching speeds in space. So we briefed the CEO of Motorola and said, we're going to have to really worry about our schedule. The Motorola CEO, Chris Galvin, just laughed and laughed and laughed. He says, you guys aren't going to be there for 6, 7 years. We're increasing our speed double every 18 months. Don't worry about it. So, you know, we don't have that confidence in the material. We're not there. But the point is, every big mega project has a little box in their schedule saying miracle required here. Now, I'm not sure we need a miracle, but we need a miracle in development, you know, money into it, work real fast, get a lot of people working and being interested. We need a lot of activity to take the material to the level we need. Yes, we have a long way to go.
Very good. I've seen that in a lot of processes, and then a miracle occurs. So
yes.
Let's see, a question from Jeff. Would fabricating CNTs or single crystal graphene be helped by making them in microgravity? Would they be larger and more pure, therefore easier to make and stronger?
Have no clue. Okay, I've worked with the people in CNTs, and they've done a marvelous job at getting CNTs to do what they need to do in electrical characteristics and stuff like that. They have not succeeded in making them long and strong yet. I'm not saying they can't, but I'm just saying they haven't done that yet. I am not an expert in that at all. I'm a mechanical engineer. I build things and break things.
Sounds good. Question from Cezanne. I'm not sure it's a whole question, but I'll read it. How can space elevators tackle the rotation and revolution? I'm not sure if that's the whole question.
Okay, the rotation of the Earth is what causes the space elevator to have the outward force which keeps the tether taut. And it's just a matter of having the apex anchor going at the velocity that's sufficient to stay above the point on the surface of the Earth. And that is created by starting at geo and then adding energy to it as you release it upward. And you got to have the upper apex anchor going at the same rotational rate as the surface location. And all the dynamics, all the people that have done the dynamic calculations of the tether, they basically think piano wire, have said that that's, you know, routine, can be done easily, just piece of cake.
Oh, very good. Got a number of comments and questions from Michael. Michael, would it be okay to allow you to talk and ask your question? Michael, I believe, is the friend of Jerome's. Let me do that.
Yes,
There you go,
definitely.
Michael. You can speak now.
Okay. I don't have a video now, but I could give you video if you let me. I don't care.
Let's see if I can do that.
That's the question
That's all
while
right.
you're at
Yeah,
it.
why don't you just go with the question? Yep.
Yeah, if you can hear me. I mean, I
Yeah, we
had
can
the
hear you. Yep.
yeah, I had the privilege of working directly for about 5 years with Jerome Pearson, and it was an awesome experience, I must say. I worked on a number of projects with him. I was actually a neighbor, and we got together quite a few times and had some brainstorming sessions regarding particularly the Mars elevator and the lunar elevator, which we ended up proposing to DARPA, I believe, or NASA. I don't remember exactly because that was a few years ago. But anyway, it was a pretty comprehensive proposal that was designed to actually fabricate the moon base with remote control rovers.
What's the question, please, Michael?
Well, and the question is, can you, the thing that is really, I think, important is how do you consider you're an expert in space debris. How do you consider the Eddie spacecraft that Jerome conceived? I worked on it with him and with John Olson. And that is designed to remove all orbiting debris in 3 years using 6 of those satielites.
Yes, yes.
Are you familiar with it?
Jerome and I were friends for probably 35 years or so. I'm very familiar with Eddie. I supported Eddie 150%. I have no idea why NASA, nor the Air Force, nor the Navy, nor anybody did not put Eddie up 10 years ago or more. Eddie is a remarkable concept to go and get debris and deorbit it using electromagnetic energy instead of rocket fuel. So we've avoided the rocket equation again. And Jerome was so elegant in talking about that, and he presented it all over the world, and it was a great idea. He should have been, that concept should have been appropriated, and we should be reducing debris today. It was not. I don't understand why it wasn't, but the Eddie concept is brilliant. Maybe somebody will take
it
and
is
run
now.
with it now.
They lofted the test. They called it a different name, but they lofted one test satellite up there, and it's working fine. I was talking with John Olson. I worked with him on the plasma problem because the problem the Eddie had from an electrical standpoint is that it generates so much energy that it's very, very difficult and very, very tricky to actually control the amount of power that is generated. The first test that was done with the space shuttle, where they just floated a tether, a rotating tether, the tether got vaporized in seconds because there was so much power.
I'm very familiar with that. I wrote my dissertation on space tethers. Do you have any more questions about space elevators?
We got a lot of others in. So thanks, Michael.
I'm sorry?
Yeah, we have a lot of other questions. I'd like to give some other people a chance if that's okay with you. Okay. Thanks for.
Yeah, no problem.
Yep,
My question is, when do you think we can actually have a space elevator? It's just a murky
2035. Is that good enough? 2035?
Thank you.
Thanks, Michael. Okay, let's see. We'll get a few others in. Let's see. Kanita asked a question of, aren't space peers a better alternative? I'm not sure what that question actually means, but maybe you do, Peter.
I have no idea what a space peer is.
Okay.
The question is, how do you beat the rocket equation? You explain that, and you can then compare with space elevators.
Very good. So let me get a few more in. Let's see what we got. Jack is asking, are there any private companies investing in this technology now?
Yes, there are many private companies investing in different parts of the space elevator. The single crystal graphene arena is getting a modest amount of money and has promised for a great amount of money. The first stage question is being addressed by a company that John Knappman, Dr. Knappman has written multiple papers on. You can see those in our website. There are other companies looking at, tether climbers and stuff like that. There are two people writing the dynamic simulation gold standard for us at ISEC and things like that. But there's not big money yet, and we're hoping for that in the near future.
Very good. I've got a question from, I apologize if I get the name wrong, Runteha. What do you think is the next biggest invention from science fiction that's going to be turned into reality? So that's kind of a broad question.
Well, my answer is space elevators.
There you go. Perfect answer. Question from Jack. Is there a difference between moving mass into space versus moving mass down to Earth from space?
Yes. I believe the first space elevators will be 99% up. The real problem is coming back down. That big gravity grabs you really badly and really pulls you down. And braking is not a real technique that we know how to work on in the sense of heat distribution. So we're really having problems. So my answer at the present time is we have one elevator for up 100%. We have one elevator that comes down, but we don't come all the way down. We go to one radius of the Earth down. So, I mean, from up, so 63, 78 kilometers above the ocean, we raise capsules up to that point, and we bring everything of value down by capsules in the atmosphere. We don't try to bring them down on the space elevator. Now, when we get to more advanced systems, maybe 2050, 2055, then we'll be able to beat that issue with electrodynamic braking instead of friction braking. And if we can get to electromagnetic braking, we can probably go all the way to the ground. But yes, there's a huge difference, and it's that big gravity well that's a bummer.
Very good. Thank you. Let me try to get two more quick questions in. I know we've got quite a few that were put in. Alon is asking about the feasibility of nuclear power plants in space, and just wanted to get your thoughts.
They're about 50 years late. We should have had them way back when. There is a set of contracts being worked on or set up with NASA for nuclear power. So both propulsion and electrical power are being discussed at the NASA level, and they're doing a really good job from as far as I can see about developing. We need nuclear power source for electricity on the surface of the moon to beat the night problem. And solar arrays are really, really good, but they are hard to get in the right place where you can get more than 14 days of light. The 14 nights in a row are a bummer.
Very good. And the last question before we adjourn, and Fred, I don't know if you could copy some of the other questions down, and we had a couple things in the chat. Maybe we can get them to Peter afterward. So because there were quite a few, and we had some great questions. Let me get this last one from Jeffrey. Space debris, likely not to be a hazard, is not the same as not being a hazard. So what happens when the random unlikely piece of debris does hit? Does anyone really think we can protect any space structure from all debris?
I believe the answer is yes, you can protect it from everything above 10 centimeters in diameter when you're tracking it. But if we have a problem, it's a problem. And if you've got a bridge over the Mississippi, or you've got airplanes going across the Pacific, you have to worry about the infrastructure. And we will be worrying about the infrastructure And hopefully we worry enough to make engineering designs robust enough that the catastrophes won't happen. But I can't guarantee that. I'm a bridge builder. I'm not a predictor of catastrophe. But yes, we have issues.
Very good. Peter, thank you so much. I think with that, we'll end the questions. We're just at our end time. And I really just want to thank you for a really interesting and informative presentation. I personally learned quite a bit. I didn't know a lot about space elevators before this, but by the way, I signed up for your newsletter. So just to learn more. So we really thank you for taking the time out. If others want to learn more too, you had that article in the most recent issue of Ad Astra. So be sure everyone to check that out as well. And it's just great to have you, and maybe we look forward to having you come back and talking a little bit more about this.
I would love to. This was a delightful time, and I love the questions. If anybody wants to send questions, go ahead and send them to the website. I see all the info at ISEC.org, so I can answer those. So if you want to send a straight question to me, that's fine.
Very good. And Peter has offered to share his slide deck. So he's going to be sending that to me, and I will put that into a PDF and send it out to everyone who's registered, along with our link for the recording. So in case anyone wants to, in case anyone's missed anything. So again, thank you so much, Peter. I also want to make sure I thank my colleague from NSS, Vice President of Chapters, Larry Ahern. We worked together to develop and put on these space forums and town halls. And of course, Fred Becker, who is our systems guy and making sure that everything works technically and does all the recording for us. So thank you all for making this all possible. Let me just go back to share the screen one more time. I will just get it into a final thank you for everyone for joining us tonight. There we go. So again, we thank you. It's great to see such a great participation in these space forums. And as I always say, the questions and comments, we have an incredibly knowledgeable membership base. And we thank you for all that you add to these events with these great questions and comments. So all of you for attending, want to thank you. Have a great evening. For those in our evening time zones, I know some people are in tomorrow already, so have a great day, and wishing you all a great weekend ahead, and stay safe. So thank you all, and we'll see you in 2 weeks.